Okay, there are still people joining, but I think we'll make a start. So, welcome to you all. Another challenging episode, this time on thermodynamics. And it's very important that you have your paper and pen there and make notes, make some jottings. Uh, make sure that you get one or two ideas that you can pick up and say, I could sort of plot that graph, calculate those numbers, and but don't sort of feel that you're overwhelmed and must do everything. No, you're going to do one thing out of this. It's one thing a week, and then you can be developing your skills. That's how people learn to do coding and this kind of thing. They try it out. They don't read a book and then go and do it. They just try it out. And that's what your opportunity is tonight. So without further ado, thank you, Dr. French.
Okay, good evening, everybody. So welcome to the BFO Computational Challenge. If this is your first visit, fantastic. Thank you very much for coming. If you've been to all the others, welcome again. Brilliant. So tonight, it's going to be some hot stuff and some cold stuff. We're going to be looking at disorder and perhaps not chaos. That's going to be another talk. We're going to be looking at thermodynamics, the physics of heat, and that kind of thing. So normally when you study thermodynamics, it has a sort of two parts to it. There's what we call classical thermodynamics and then statistical physics. And essentially, it's kind of before the idea that we are comprised of atoms in jiggling tiny atoms, billions and billions of them jiggling around in random motion. Possibly the largest and most important idea of physics, you could possibly argue, that we are made of atoms. And this sort of idea of working out properties of trillions and trillions of atoms, pressure, temperature, entropy, that's something that would be kind of more of a modern physics course. So what we're going to do tonight is we're going to look at the kind of before the bit where everyone agreed that atoms exist, looking at classical thermodynamics of how pressure, volume, temperature, and entropy interact with each other without having this sort of idea that really it's made of tiny particles. And then we're going to look at the sort of motion of tiny particles, random walks, and that kind of thing. So that's the kind of split. So as Mr. Hughes recommended earlier, we're going to be looking at little projects that you can do. So we'll talk about a little bit of physics theory, and then I will sort of pause at various points and go and suggest, well, maybe this could be a really good project for you to do. All right, so let's make a start. And please put some questions into the chat, and hopefully I will be interrupted at suitable points to ask your questions. Okay, so let's go. So firstly, a plug for this book. Just to sort of, I have no connection with Theodore Gray. I just happen to own all of them, and they are absolutely amazing. So if you fancy a Christmas present, these are utterly beautiful. And he's, I think he was a chemist originally, and ended up working with the Wolfram Alpha sort of algebra system. So he's written these books on the elements, molecules, reactions, but more recently on engines. So these books contain fantastic photographs of all sorts of engines and things. Apparently, he bought a laser cutter and bought, I think he lived in a sort of what used to be an old bank in the middle of America somewhere. So he cuts things up and gets his friend to photograph them. And so anyway, just amazing stuff. So if you are interested in some of the engines we're about to talk about and what they actually look like, you can see if you can get this book in the library or perhaps buy it for yourself. Very good. Anyway, so let's kind of have a look at about engines. So firstly, some kind of key ideas, and if I can zoom in here, let's have a look. There we go. Right, so we've got this idea of a heat engine. All right, so essentially, pictorially, this is what it looks like. So we've got a reservoir, some sort of large quantity of, well, these days we think about it as jiggling atoms. And if we extract some kinetic energy from that, it doesn't really make a difference to the average kinetic energy of the molecules. And that's what absolute temperature is. So temperature in Kelvin is proportional to the mean kinetic energy of molecules. So that's one of the big ideas that relate thermal stuff to things like mechanics, like sort of half mv squared for kinetic energy. So that's what a reservoir is. So we've got a hot reservoir somewhere, and then we extract some energy from that, and we do some work. All right, a force times distance moved in direction of force, that kind of thing. And we're going to call that a heat engine. Now, what is that in practice? It's going to be pistons, it can be all sorts of things, pumps. But before we actually get down to the details of what an engine could be, the sort of thing that's, so we've got some combustion engine. I think that might be a diesel engine. That's a sort of Stirling engine. That's an electrical motor. It looks like a sort of engine for an aircraft, something like that. It's obviously a motorbike. All right. These all follow, although they look complicated, follow similar principles. And so basically what we're doing in this is we're taking some energy from a hot reservoir and we're doing some work with it. And then we are transferring some energy to a cold reservoir at temperature T cold. So T cold is less than T hot. Now, you may think, wouldn't it be great if all the energy we could extract from the hot reservoir, we could then turn into work. We could extract some energy from burning stuff or however, we're generating some energy. But it turns out that's not allowed, right? And the reason is because of the second law of thermodynamics. So let's talk about some really basic sort of fundamental physics equations here. So the first law of thermodynamics, relative to this picture, and if you've seen my sort of talks and lectures before, you'll know this. One of my key kind of nags, if you like, is that you've got to define your universe. Right? It's like in maths, really, because it is maths. You're saying, okay, let's reduce the world to this simple problem, and the variables I define, I now interact mathematically, and I use those variables and nothing else. This is really why we start with diagrams in all physics problems. Okay, so the first law of thermodynamics, that energy is conserved relative to the universe I've defined here, this kind of slightly abstract heat engine universe, means that the input heat, so the thermal energy, the sort of total kinetic energy I can extract from my hot reservoir, is equal to the heat that comes out plus W, which is what I'm going to call the work, the useful work done. All right, so that's the first law of thermodynamics. Okay, now something more interesting perhaps is the second law. So before we talked about the idea that atoms exist and statistics, entropy was defined as a heat change divided by an absolute temperature. So it's important now that that's in Kelvin, not in Celsius, or certainly not in Fahrenheit. Okay, so 0 Kelvin means 0 kinetic energy. All right. So we can look at the entropy change of my reservoir and the entropy change of my cold reservoir. So we're extracting some heat from my hot reservoir. So the entropy change is going to be minus Q in, whatever that is, divided by the temperature of my reservoir. And we don't need to sort of sum it up in a calculus way because it's a reservoir, we're saying that the temperatures don't change when we extract something from it. That the amount of heat we take is a measly amount compared to what's available here. It's like trying to take a drink from a lake, unless you're very, very thirsty, you're not going to change the lake at all. So there we are. So what we can do is work out the total entropy change of my universe, which I've defined to be this system. So if we add those two things up, we've got this little expression here. Now, the second law of thermodynamics, and I recommend the Flanders and Swan song to explore that. I'm not going to sing that to you, but you can look at that on YouTube, is that the total entropy change for any change you can think of must either be 0 or bigger than 0. It cannot be negative, and that's the whole universe, right? So you can think of systems, endothermic and exothermic reactions in chemistry, where part of that system might have a negative entropy change, but it only works if the total entropy change is bigger than 0. And for those of you studying A-level chemistry, you can put your hands up, your virtual hand up, so you're doing A-level chemistry. That would be awesome. Can you put your hands up in the chat, as it were? Do you have any chemists? I'm sure I can see that, actually. Maybe I can't see that. Anyway, hopefully there's lots of hands. So anyway, so in chemistry, you things like the Gibbs free energy, but ultimately we're looking whether the total entropy is bigger than 0. If we're understanding whether a reaction will work. So if we say that to be true, this quantity we calculated must be bigger than or equal to 0. Right, now what we're interested in a lot of when we're designing engines and analysing engines is to look at its efficiency. So what we're going to define as efficiency, and I'm going to use the symbol eta for this little symbol here, is going to be the work done, W, by my heat engine, divided by the heat input. So ideally, wouldn't it be great if that was 100%, that was 1. So W equals Q in. But that's not true. And this is a way, without doing anything else apart from looking at this, our first and second law, we can show why that cannot be true. So what I'm going to do is I'm going to replace Q out by Q in minus W, just by this one here, the first law. So I'm incorporating the first law into the second law. And when we're doing any form of sort of physics derivations, what you do in maths when you're combining equations is you're literally combining the laws of physics. So I've baked in to this the first law and the second law. So this expression now should tell me something interesting about this system, because now I've incorporated both first and second laws of thermodynamics. So what do I really want? I want to work out W over Q in. So let's go and do a bit of maths. I divide both sides of this by Q in. All right, I've got a 1 minus this one. And I've got a minus 1 over TH here. And it might make sense to then sort of maybe multiply both sides by TC. So I've got just that little sort of fraction here. And then if I put everything to the other side, what I end up with is that minus TC over TH plus 1 minus my efficiency, eta, is bigger than or equal to 0. And let's just tidy that up. Let's eta on one side. So therefore, my efficiency must be less than or equal to 1 minus the ratio of my reservoir temperatures, and these are Kelvin. All right. So, for example, if my cold reservoir was, I don't know, 273, well, that's a bit harder than that, 283 Kelvin, a cold lake, and my hot reservoir was, I don't know, 373 Kelvin, we could work out 1 minus that is what the maximum efficiency of my heat engine could be. And look at that, as that ratio gets, I guess, as T hot gets much, much bigger than T hot cold, that fraction gets smaller and smaller and smaller, and eta gets closer and closer to 1. But however we do it, we can't actually have eta to be unity. All right, because there will always be, it won't be infinitely hot and very, very cold. Okay, so isn't that cool? So we've just literally defined this picture, not said anything about how our heat engine is going to work, but by using the first and the second law, we can show that this is the maximum efficiency of any heat engine. So the next plan is to look at some real heat engines, or sort of real heat engines, some realistic heat engines, and compare that to our maximum efficiency. So what we're going to look at, and this is, if you do a course in thermodynamics, this is not particularly way out at all. We're going to look at something called a Carnot engine, which is as efficient as it can be, but pretty hard to actually create it in real life. But it will give us a sort of template for how we might model a heat engine. And then we'll look at a diesel engine and a petrol engine, which hopefully in your lifetime will go out of favour. But sadly, it all exists these days. But nonetheless, I think it's very instructive for us to analyse it. Most of global trade is via sea, and that's using of diesel, very, very efficient diesel engines. Maybe we'll have sales in the future, but at the moment it's a diesel engine. So let's sort of look at some of these. There's a bit of details here, so I think it's important to kind of look at the essentials, and then if you think this is a nice project for you, to code it up. All right. So I'm going to give you a kind of a tour of how this works, and every heat engine we'll look at will follow a very similar recipe. Okay. All the various details I think I would download from this presentation. Have a go yourself. So let's get basics first. So we talked about work. So when we're looking at heat engines, a practical one, we're going to talk about pistons and using gas. So it's what we call a kind of, a sort of gas model. So we are compressing gas, expanding gas, igniting gas, heat, changing, exchanging heat with gases in sort of finite volumes, etc. So let's have a look at how work relates to pressure and volume. So if we've got some sort of cylinder here, we apply a force to it. All right. My volume change is going to be the surface area, A, of my cylinder, times dx, which is my change in the sort of height of my cylinder. All right, which might contain some gas. So the work done on the gas is the force times a little bit of distance. Okay. So mathematicians amongst you, I know I should be using little deltas here. I'm just going to use the calculus notation because that's, we can make that differentiably small. It's a small quantity. So now force is going to be the pressure times the area. And my dx will be my volume change divided by the area, because my volume change is going to be the area times dx. I hope that makes sense. So if I put that together, my area is going to cancel, and my amount of work that I do on the gas, okay, not by the gas, on the gas, is minus PdV. All right, so the pressure times the volume change. Really useful idea that. And so if we look at the first law applied to this system, right, if we apply some heat to it, all right, and we do some work on it, right, what's the change in internal energy of my gas? Well, the heat plus the work done on it. So dq minus pdv. If you're bothered about the minus sign, remember dv in this case would be negative. So that's like on a double negative. All right. So there we go. So that's the sort of first relationship involving internal energy, heat, and work, or what involves work. And we can also relate internal energy in terms of absolute temperature. So this is, I guess, this links to the modern concept of thermodynamics, which is the temperature is related to the mean kinetic energy of molecules. I guess in this we're kind of glossing over that, because there might be some potential energy too. But if we're talking about gases, ideal gases, we don't really care about the stickiness of the gas. All right, that's the ideal gas model. So this is pure kinetic energy. What's the constants? Well, this is called the molar gas constant. That's the number of moles. And then we've got some numbers in front. And so this might appear strange and mysterious where this comes from. I'm going to leave that story, the details, to some books and resources I can point you towards. But essentially, this is what defines internal energy in terms of temperature. All right, so an interesting mystery for you to look at about why it's a half there. But anyway, so if we've got molecules, they can move in X, Y, and Z. And so that would normally be 3. But you could have stretching, you could have rotation. So the number of degrees of freedom of molecular motion could be more than 3. But for most gases, the internal energy is 3/2, number of moles, molar gas constant, times the absolute temperature in Kelvin. Okay, so that's what relates. I suppose that's almost a kind of, you could almost think of that as a definition of temperature involving the mean kinetic energy of molecules. Okay, right, so we're going to put this together. We've got a few other things which are going to be our basic ingredients. All right, so we've got this idea of the ideal gas equation, and lots of you will have met this before. The idea of pressure times volume, number of moles of gas, molar gas constant, and absolute temperature in Kelvin. So, you've got Boyle's law. If you take a cylinder and compress it really slowly, isothermally, so T is the same and it doesn't leak, then PV is a constant. So P is inversely proportional to V. Fantastic experiment if you've not done it. You could have what I did literally yesterday with my class, where we had a fixed volume of gas and we heated it up. And then we saw that P goes is proportional to temperature. And if you do it in Celsius, extrapolate it down to work out when P is 0, you'll get minus 273 Celsius is corresponding to P is 0, so absolute 0. So you can heat a gas up in a lab and you can work out the temperature that your gas would stop moving, absolute 0, which is a pretty cool experiment. So there we go, that's one ingredient. And then we've got the Clausius, this is Rudolf Clausius, who defined our entropy, a change in heat divided by the temperature. So when you're looking at some heat cycles, the idea is to look at different processes where some things are constant. So the first one usually is an isothermal process. This is when T is a constant. All of these processes, we're assuming we're not leaking any gas. We've got the same number of moles of gas that we're using in our cylinders. So for an isothermal process, we can use this equation and the first law of thermodynamics, so this one, to work out a few things. Again, I'm going to gloss over some of the calculus details. I'll leave that as so this is going to be kind of think of as a recipe. The idea that PV is a constant. All right, so in a pressure volume diagram, that's going to be a hyperbolic curve. And if you work out the heat change, remember it's PdV. If it's isothermal, the internal energy is 0. The internal energy change is 0, should I say. So the heat change is going to equal PdV. So if we integrate that up, if P is going as 1/V, you're integrating 1/V with respect to V, which gives you a natural logarithm. Okay, so if you've not done it in maths yet, then just take my word for it. But a lot of you hopefully will be nodding sagely that you've probably just done this or did it last year. So you can work out the heat change and of course the work done, because it's so this would be the work done by the gas. All right. So an isothermal process, we put Q joules in, and W joules is the work done by it, all right, in that particular process. So you're thinking, hang on a minute, surely this isn't possible, Dr. French, because we're not allowed to break the first law of thermodynamics. Well, the reason is that this is just one part of a heat engine. So overall, all right, we might sort of have a negative entropy change, but over the whole cycle, we will satisfy our second law of thermodynamics. So that's the formula for the heat and the work done, which goes as a natural logarithm as our ratio of our volumes. We can look at a slightly more interesting one. This is a isentropic process, and this is where entropy is changes is zero, so no heat is exchanged. All right, so that's quite hard to actually achieve in reality, but you can kind of imagine a system where you're maybe expanding a gas, but just no heat is added or removed from it. And in this particular case, it turns out you can work out that PV to some constant, gamma, is a constant. So it's not quite the same as PV is constant. And that constant gamma is the ratio of specific heats, which is, you think it's heat capacity. So if I sort of add some energy to something and it goes up in temperature, either at constant pressure or volume, the ratio of those constants is what this is. And it turns out it's also related to that degrees of freedom. So for molecules bouncing around without any rotational stretch, alpha is 3. So 1 plus 2/3 is that ratio. And if you work it all out, just sort of putting into this equation, you can find out, there's a little bit of work to do, but you can work out an equation for the work done. Remember, there's no heat change here. So that's I would take this at the moment as a recipe book. So this is how you work out work done, P versus V. Now let's put it together into a model. So this is called a Carnot cycle. Let me have a look at this. So this is how I think I'll start it, actually, in a plot that might be strange. So what we're going to do is we're going to plot, if I make this nice and big so you can just see, and I'll obscure the maths just for the moment. How do I move that out way? Right, here we go. Let's make that as big as possible. Right, so what we're going to do, this is a Carnot cycle, and my hot reservoir is 90 degrees Celsius, so that plus 273 Kelvin. And my cold reservoir is 20 degrees. And I've got a cylinder which is a tenth of a cubic meter, so fairly reasonable, sort of 10-litre cylinder, something like that. And this particular cycle, that you can calculate that the efficiency is 19.3%, the input heat is 72 kilojoules, and the work done is 13.9 kilojoules. How have I done this? So the first thing you're going to do is look at temperature versus entropy. And this may seem a very bizarre thing to do, but this defines the processes that form our cycle. So all of these engines, if you think about it, an engine, you're taking in some gas. In fact, let's just have a look at an engine cycle before we go back to this, like a real one. I've got a few lines down here. Let's go and find one. Here we go. So here's an engine. This is like a sort of well, it could be a diesel or a fuel one. Kind of depends how it works. But you've got a sort of cylinder here, and this sort of mechanism is a sort of, I'm not quite sure what you'd call it really, but this sort of rotates, and as this thing rotates, it pushes the cylinder up and down. So this sort of contraption at the bottom allows you to have rotational motion turning into up and down motion, all right, which is the sort of big kind of Victorian innovation. So you draw in your intake, so you open a valve here, air is sucked in, and then you compress it, and then if it's diesel, you can press it enough so it actually ignites and releases heat. If it's petrol, you have to apply electrical signal to make a spark, which ignites the fuel vapors, and then it will, that will release heat and explode. And then what will happen is you'll do some work. All right, it will expand, do some work, and then you'll actually release your heat here, release your exhaust fumes. You can draw some more air in. So I guess although the number of moles is retained, it's probably not the same moles, because you want to remove your pollutants. But essentially, it's a cyclical process. Okay, and this stroke here is where you do work. So you're using internal energy of your fuel to push a piston, which will then, drive some sort of push a rod, which will turn a wheel or something like that. Okay, so we need a cycle, and what we're going to have a look at is one of those. So the Carnot engine, which is the most efficient you can do, is where we have 4 processes. And the first one is an isothermal expansion. So what does that mean? It means we're expanding a gas at constant temperature. And so in this particular case, we've got a hot gas. All right, so it's at 90 degrees Celsius, and we increase the volume from 1 to 2. All right. Now, then what we're going to do is we are going to expand it a little bit more, but without any heat added. We call that an isotropic expansion, a constant entropy expansion. Now, if we plot a graph of temperature versus entropy, that's really easy to do, because if you've got isothermal, then we've got horizontal lines. And if you're isentropic, then we've got vertical lines. So without knowing anything about, we don't have to do any complicated maths. We could just draw a rectangle. And so once we get down to 3, which is now a lower temperature, so we've expanded our gas and it's cooled. So the work done by my gas is paid for, if you like, by the reduction in temperature, internal energy of my gas. And then we can compress it isothermally, and then we expand it isentropically, and then we start again. So how can we work out all these useful things? So if we have a look at the first law of thermodynamics, that's dq minus pdv. So this is where we had it before. Now, dq is the temperature times the entropy change. Remember Clausius's law. So TdS is dq over T. And this allows you to make a really bad pun. You can talk about that thermodynamics is really TdS. Right, TdS. Anyway, never mind. I think Professor Chung is probably hitting his head at the moment, I think. So there, TdS is the heat change. And we can leave PdQ. So if we go around the whole cycle, all right, then the internal energy is going to be what it was before, going from 1, 2, 3, back to 1. So that's what this little symbol means. This is an integral. What we're doing is we're summing these little changes. So if we find out the total work done all the way around the cycle, that's PdV. Remember, this is the work done by the gas, not on the gas. Then that will equal the total sum of, well, the integral of T with respect to entropy. There should be a capital S there, I've just noticed. And that's because that TdS is PdV if du is 0. Now, this is quite interesting. So what is that quantity? Well, if you think about it, it's going to be the area enclosed, well, that one is, in that graph. And if we plot a graph of pressure versus volume, that quantity is the area enclosed by that curve. And we'll see one of those curves a bit later. So that's a really easy one to do, because that's just the area of this rectangle. So the total work that we can do is literally the area of this rectangle in temperature entropy space. And because we're doing a difference in temperature, it doesn't matter that that's not in Kelvin, right? Because the increase in Kelvin is the same as an increase in Celsius. So there we go. If we work that through, that's the work done. And that's our entropy change. And we can work out the entropy change by the heat input divided by the temperature. And because that's an isothermal change, right? Isentropic changes don't have any entropy change. And we said the heat was this logarithm thing. What we can do, by dividing it by the temperature, we get this quantity. So that is the entropy change. We can work it out. So you can work out delta S, and of course it's the same, it's a gain here and a loss here. And you can then work out what my efficiency is. So what we can do is we can sort of use, that's for Qin, and we can use this sort of process, and essentially we can divide this lot by this lot here, and you'll notice the logarithms cancel, and you get 1 minus Tc over Th. So if we could have an engine which looks like this, then this would be as efficient as it could possibly be. Okay, so before I continue, are there any questions that we might want to pop up? Kimlan, we've got any in the chat?
Not really, no.
Right, so you're thinking, right, okay, well, in terms of projects, well, firstly, for a Carnot engine, you could plot this up and you could work out the numbers in the title here. All right, so that's working out, well, you know the efficiency, but you could do the energy change here. So essentially this one. and you could work out. So that number we've got there, if we know TH and TC, we know N, we know the volume change, we can work out these. All right. So let's have a little look at what we might do in terms of pressure and volume. So this is what, in practice, because entropy is rather an abstract thing, this is what the Carnot cycle actually looks like. So there we are. That's the rather dishy Nicholas Leonard Sadi Carnot in his military uniform there, 1796 to 1832, and I think we credit him for working this out. So what are we plotting? Because it's quite busy, this picture. So let's work our way through. So what we've got is the same process, exactly the same numbers, but we're starting off at a certain pressure. Okay, so what's kind of hidden from this, and perhaps I should have in my my title here, I need to start off what that pressure is. So I'm starting off at, say, I think it's about just over 10 atmospheres, something like that. So what I'm going to do is we are then going to go all the way down. So that the graphic means pressure volume. So I'm plotting this as volume divided by my initial gas volume here. So we need to kind of keep track of what our inputs are and what we can calculate. So this red line is an isothermal expansion. So constant temperature. All right. And so in order to get it to expand, we've got to put some heat in. All right. So the heat input basically increases, if we expand it, if it's isothermal, our internal energy must remain the same. So basically heat input accounts for all the work that's done in expanding this thing. So we get to position 2, and then we allow it to keep expanding, but now with constant entropy. That's the green one. All right. So what we want to do is work out those curves. So remember, PV is a constant for this one, and PV to the gamma is a constant. And that's where we can work out these curves here. And then we've got an isothermal compression, where we're basically releasing heat, and that takes into account our work done by the gas. All right. So the gas loses energy, and the energy goes as heat. And then we do an isentropic compression at constant, so no heat is exchanged. So the idea is you want to work out what the pressures are, what the volumes are at all these points, and we've already calculated the heat exchanged and the work done, which is the area under this. That's quite nice, because that sounds like a horrible thing to work out, what the area under this sort of shape is. So that's why plotting it in this temperature versus entropy space is a much better idea. Okay, so there we go. Let's look at our inputs and how we might plot this. So our inputs are going to be the reservoir temperatures, T hot and T cold. We need the original volume, and we also need the volume 2. So this volume here. So our kind of compression ratio. We also need the moles of gas. So if we know all of those, in fact, we actually don't even need to work out the pressure in that case, because PV is nRT. If we know the temperature, we know the number of moles of gas, and we know the volume, V1, we can work out P1 is nRT1 over V1. All right, so we're using the ideal gas equation at all of these points to figure out everything else. And then for our various processes, and this is an instrument we want to derive, but you can work out volume at volume 4 in terms of volume 1. And that's just sort of combining all our equations together, the ideal gas equation and our sort of isentropic PV to the gamma as a constant. So that's for you to do in slow time. But ultimately, this is a recipe. So what we could do is maybe code this up. So here's an Excel sheet. I think you can download this in the Eclecticon, but it's worth having a go yourself. So this is a Carnot cycle, and this graph, in fact, I think we'll just deal with this one at the moment. This graph will move as you change your inputs. So what do we got? Is that big enough to see? So here we go. Here are my inputs. So hot reservoir, cold reservoir. I've got the mass of gas, and I've worked out what the number of moles is basically from that. So I've got the mass of gas. I've got the volume of gas in litres, so V1 and V2. I've got the number of degrees of freedom, the molar mass of gas, and then I've worked out, these are all calculated in kilojoules, my heat input, output, work done, entropy change, etc., and efficiency. So this is about 30% efficient, something like that. Okay, and how have I plotted the graphs? Well, what I've got is all the 4 stages. I don't know if you can sort of see this nice and big. There's a nice technique here, which I want to show you. So if you want to plot any sort of graph of something which varies, so rather than sort of having an increment of, say, volume or pressure, what I'm doing here is I've got some fraction 0 to 1 in, I think it's 100, yes, and 0.01 steps. So that's my volume fraction. So what I do is that defines my range. And these volumes here go from V1 to V2, V2 to V3, V4 to V1, etc. So I'm working out my volumes, so my coordinates of each of these points. And then I can use my graph to work out a linearly spaced vector of my volumes from here to here. And then I can use the ideal gas equation to work out my pressures. So that would be a really nice thing to do. It might, if you've done this for the first time, you'll make a mistake and you'll scratch your head. But it is a really rewarding thing to actually get the whole cycle to work. So I probably start in Excel because this is the structure. And everything is all there. You can see you've got P versus V for your different sections. You're working out the coordinates from here. There we go. Those are my coordinates of P1, V1, etc. Everything is all there. And you can use color. I like using color to define inputs and differentiate those 2 outputs. All right. And if you've got, if that's pretty good, then you can do it in Python or MATLAB or something like this. So anyway, that's a really nice project, which I'd recommend. So any questions before we move on? Because I'm going to talk about some other types of engines now. Any questions, Kidman?
Is there an efficient way to input those values into the table?
Right. So what are we talking about the big one on the right-hand side, or are we talking about the little one here?
I think it might be the big one.
Right. Okay. I think if I can find, I'll see if I can find the simulation itself, and then we can answer that question more accurately. So let's have a look. Physics. I'm going to delve into my computer now. Let's go for thermodynamics. Let's go for simulations. Let's go for heat cycles. Carnot cycle. Here we go. Let's see if it's this one. Yeah, that looks about right. Okay, so this might be hard to see because I'm going to have to sort of click in the corner here. So what I've got is, there we go. So yeah, so in this big table here, my volume, so that starts off, so C29, which is C29, this one. So what I do is I work out my pressures and volumes of all my coordinates at this point. So 1, 2, 3, 4. And these are, it's quite hard to read the formula because it's Excel speak. But basically, the equations which say in the recipe work out these points. And then what I do is I kind of have my volume. So my pressure is using the ideal gas equation. And my volume goes from V1 all the way to V2. So if I click in this cell, it's got the first one, C29, so that's V1, plus T8, which is the fraction of the V1 to V2 change, times V2 minus V1. So what we're doing there is you're going, okay, that this thing here is the fraction of the change between V1 and V2, or V2 and V3, or V4 and V1. And we're adding that to the start. So it's what we call a linearly spaced. If you plot it on a graph, this would be a linearly spaced change between the two. So 0.4 is that one. V2 is 1. So if I scroll all the way down, you'll see that's 1 at the bottom. All right, so I never need to change this table. And the secret is doing this little fraction here. I wonder if maybe I could do a very simple example, if that's not very, if that's too complicated. So if I make a new Excel sheet, new, right. So let's say we're going to plot, I don't know, we're going to go from, let's have an example now. Let's have a fraction, 0 and equals the previous cell plus 0.1. So I'm going to go for 10 steps. Let's make this nice and big so we can all see. All right, so there we go. There we are. Right, so now let's just say I'm going to define some sort of length. And what I want to do is I want to plot y versus x squared over that length. So let's have a look. Let's call my width. Let's call it a equals, I don't know, 10, for example. So my x values are going to be all the way from 0 to whatever this happens to be. So if my x values, that would be equals this one multiplied by whatever this cell is. In fact, let's give it a letter. Let's call that A. Will that allow me to do that? Yeah. So I've got that cell there. Let's call that A. This is going to be my fraction times A. If I drag that down in Excel, right, whatever that is, let's call that 12. I go from 0 to 12. Let's call that 7. I've got 0 to 7. All right. So this is a way of defining a vector, linearly spaced vector of values based on what the maximum is going to be. Okay. And then I could do a little equation for this. So y equals x squared. All right. So equals that one squared. All right. There we go. And I could then plot that, insert scatter graph, right click, select data, add my x values are going to be this over time, right? And my y values are going to be this one. Oops, wrong one. So wrong one, sorry. Let's get rid of that. Yeah, and my y values are this. There you go. So we've got a nice sort of quadratic variation there. Let's put some axes titles. The point is, let's go for y. The point is that if we change this, then that will change my graph. 100. There you go. All right. So it's a really nice sort of paradigm. Okay. So I'm just going to sort of gloss over a few of these little things. So that's a Carnot cycle. Let's have a look at how you might do an Otto cycle. So this is for a petrol engine. Here's a little sort of Ford engine here. And so it's a bit more complicated, this, but it's the same idea. So I think what we'll do is we won't talk about the actual mass. You can use that for your recipe. Let's just see if we can understand the graph. So an Otto cycle is where we basically take something in at atmospheric pressure. All right. We compress it adiabatically. It's the same as isentropically, so without any heat change. And then what we do is we increase the pressure by adding heat at constant volume. That's quite a different process. So this is more like what happens when when you basically put a spark into some fuel, that goes from position 2 to 3. So it increases in pressure rapidly without changing much in volume over a very short time scale. So that's not a bad model for how a petrol engine works. And then what you do is you get it to expand and push your piston without any heat exchange. And then you basically take it down at constant volume again so by releasing your fuel. And then that will be you're dumping your heat. So the air under this graph is the work done. So, and if you work it all out, you can look at the efficiency, which is interesting to this. It's 1 minus 1 over the ratio of your volumes to this sort of power here. So you can make a little Excel sheet, and very sort of similar. This is a diesel cycle. This enormous engine. There's probably larger ones now, but when I made this, I think this was the largest container ship in the world. Absolutely massive. The engines, I think it's might have about 4 of these engines, and that's a person, 1 meter 85, a bit taller than me. And look at the size of that thing. So it's huge. So a diesel engine works in a slightly different way. So what you do is you take things in here and you compress it adiabatically, i.e. with no heat exchange. But now we expand it, so we add some heat, or rather the heat is released from your compressed fuel, and you increase in volume at constant pressure. It's what we call an isobaric process. So that's different. That's different from our Otto cycle, where we sort of increase in pressure but not in volume. So again, this is not really exactly what happens in reality, but it's not a bad model. And the difference is your heavy fuels for your diesel, you're not having to add a spark. It will, if you compress it enough, it will combust. And there we go. So we're going to work the work done. We need to work out what these curves are, and we're using the ideal gas equation to do all that kind of stuff. So again, the actual derivation of the work done is a bit more involved for an Otto cycle, but essentially it's the same process. So there we go. Some models here of heat engines: a Carnot, a diesel, and an Otto cycle. There are lots of others you can look up on the interweb, but essentially it's the same process of working out what these curves are, and the entropy change, the work done, heat inputs, etc. So give that a go. Right. So I'm just going to skip across that slightly. Right. So we've got a few minutes left. So I'm just going to sort of show you a few little paradigms. I might leave this one for another day. In fact, we tend to talk about Newtonian cooling at the Olympiad sessions. So I think if you haven't been to those sessions, this is mysterious. Perhaps you can come next time or have a look at this yourself. So I'd like to just talk very briefly about some sort of random nature of heat flow. So this is what you will learn in school about the nature of random jiggling of molecules. This is Robert Brown, 1773 to 1858, and loads of nice simulations. I think the best one I've ever seen is I think it's done with the IOP. You have a big kind of cylinder where you put some ping pong balls in it, and they represent the air molecules, and you have a big sort of slightly flaccid a balloon with some water, and that represents a smoke particle, which you look at under a microscope. And the idea is that a smoke particle kind of jiggles around randomly, and the reason it's doing that is it's jostled by the smaller particles that you can't see. So Robert Brown looking at sort of pollen grains. You might do it looking at a smoke cell under a microscope. So the idea is it's sort of random motion. So you can think about sort of one of the models of molecular motion being what we call a random walk. And the way you might want to start here is not in 2 dimensions, but 1. And you could say, okay, let's say I can make a kind of step forward or backwards. And my step size is L, and I can move backwards or forwards, and it's completely random. So my total displacement is the sum of a random string of -1s and 1s, which is this. And what you might want to work out is the root mean squared displacement. How far do I go? Now, the notation might look scary, but it isn't really. It's just a sum. So what we do is we square this quantity and then square root it. And that gives you an idea of how far we've gone, because we might have negatives and positives. If you expand that thing out, you'll notice that we've got the squareds of all of these things plus the cross terms. And because there's likely to be as many negatives as possible, all that stuff becomes 0. So what you find is that the sum of all of these lot, this thing here, is just the number n. So that means our root mean squared distance is predicted to be the step size L times the square root of the number of steps we've got. That's quite interesting. So why is it, where does the square root come from? Because of this. So I've got a little simulation. And you can relate that in terms of sort of molecular speeds as well. But let's just have a look. So your step size, you could think about being the mean free path. So how far do you move in a gas before you hit something? So here's this is a little simulation I've done in Excel, where I've sort of done this. I've run this over thousands and thousands of steps. And although it's quite a sort of jiggly line, this is the square root of n. This is the step number. And it will follow this. And in fact, if you average over many iterations, it will follow it very nicely. I've got a little simulation here. Let's skip that for the moment. Let's skip that. Let's skip that one. And there we are. Let's go to the Excel sheet. So there's quite a few things you want to look at. So what I've done is I've got, here's my step size. This is the square root of n. And what I've got, say, 12 random walks, which are happening simultaneously. And so if you notice, I've got 1s or 0s here, and I'm kind of cumulative adding them up. So 0, 1, 2, 3, etc. Some of them are negative. And if we work out my root mean squared, so I square x, and I do the RMSX, averaged of all of these, and what I end up with is this little curve. The higher the number, the closer I'll get to this sort of ideal. Okay, so we've got about 5 minutes left. So this is perhaps amazing, but abstract to you, just going in one direction. Wouldn't it be great to actually have 2-dimensional motion? So this is perhaps my second tip for a really good simulation. If the heat cycles, that's a really good thing to do. If that seems a bit involved, try this. So that's it in Excel. So I'm going to skip to this. So this is a 2-dimensional random walk, and it's really easy to code up. So we start off at the green spots here, and we end up at the red spot, and there are 10,000 iterations. The step size is 1 unit. Okay. So how does this work? How do we work out this? So you could do this in Excel, but it really is a lot easier in a program that has a loop to it. So this is the MATLAB code to this. So what do? We're going to define the number of steps. Let's call it 1,000,000 in this particular case. Let's go for so I've got a bit more detail than the one you used to see. Let's have my step size to be 1. And I'm going to initialize a big old vector. Think about like a column in Excel. And then what I'm going to do is I'm going to step through that. I'm going to work out what happens next. So this is my loop. I'm going to loop around 1,000,000 minus 1 times. And that will happen very, very fast. So I'm going to find an angle this time because it's 2D. And it's going to be any direction I like. So rand is a number between 0 and 1. And so anywhere between 0 and 2 pi radians is going to be my angle. Okay, so you can imagine I've made a step and I've sort of, spun a compass randomly. Right, I'm going to go that direction. So then what I do, so S cos theta is my x displacement, and S sine theta, if you think about drawing that, is my y displacement. And I'm going to add that to my previous x and y value. All right, so that starts off everyone thinking zeros, and I'm going to work out what the next x and y value is as I go through. And that's it, basically. That is all your simulation needs. And then I've just got some plot commands to make this picture here. So that's quite pretty. And then I've got something that prints it out. So that's a really quick thing to plot. It will take you 5 minutes if you know the language, a bit longer if you need to look it up. So you can use matplotlib in Python. Other languages are available. So a slightly prettier version of that is to function it up. So this whole thing becomes a function. And then you might plot it several ones on top of each other. So this is about 50 or 100 random walks, each one with a different color. And I think this looks like a work of art, really. You know, this is this kind of biological. Yeah, this would be a nice thing to do. So there we are. I've got just literally a variety of random walks, which I've created, and all following the same sort of statistics. So there we are. There we are. So this is sort of how that's working. So I've got a random walk, and my P loop is the number of random walks. So I've got a loop within a loop. So my random walk generator is what you saw before. Okay, so it's quite easy to code up, but I've defined a function which gives you your x and y coordinates based on the number of iterations and your step size. So there we go. I think that is probably enough for today. The next step will be look at something called Boltzmann statistics, but I think that will be that's very much another lecture. So in summary, we've looked at 2 things. We have looked at heat engines, classical theory of heat, pressure, volume, temperature, and how that might work in a cycle. And we've started to look at just one lens at random motion of molecules, which really is what's the source of all of this stuff. That's where the kinetic energy comes from. The mean kinetic energy of molecules is proportional to temperature, and the motion of that is random. So there we go. That would be a really good start for thermodynamics to code those up. So Dr. Chung is going to talk to you about an opportunity for some of you.
Yes.
And
can you hear me? And you need to unshare your screen so I can share mine. So if you are in year 13, so Andy, can you see my screen?
I can indeed.
Okay, wonderful. So if you are in year 13, we are looking for potential students who could be interns over the summer. So these are students in year 13. They need to be students who will have finished school, because we can't have them be privy to some of the questions that we might be dealing with going forward. So we're looking for a few students to help us with producing the papers database. So you might be aware that papers.bpho.org.uk exists as a mechanism for you to search for particular topics and particular exam questions that we've used in the past. That was only for round 1. What we're looking for are people who can help us LaTeX and typeset, produce diagrams, write solutions, typeset solutions for other competitions that we run. So this includes the AS competitions and the GCSE competitions. So you'll be learning how to do this in LaTeX. You'll be checking the physics content. You'll be working as part of a team. You'll be producing diagrams. What we're interested in are people who are keen to learn. So if you know LaTeX at the moment, great. If you don't know it, that's fine. You'll be taught what you need to learn and then use that. This is a flexible internship. Dates are minimum 2 weeks up to 2 months. Longer preferable, depends on the amount of work we can assign you. The start date will be after your A-levels. So this is early July, and it's remote work with flexible hours. If you are interested, please email me on anson@bpho.org.uk, and I want to see your CV and a 150-word cover letter explaining why you might be interested, your skill set, including typing speed and any previous LaTeX experience, so we know what we need to do. Deadlines for application will be in 2 weeks' time, so 15th of March. And if you are shortlisted, we'll interview you after the Easter, actual Easter break. So it'll be in April sometime. Okay, so dates to be decided, depends on the shortlisting process. So if you're interested, do let me know. You've got 2 weeks to apply. Thank you.
Right, I think that's it. Thank you very much indeed. See you next week.
Q&A, etc. left to go.
Yes, I'll take any questions.
Yeah. So webinars are directed for anyone who's interested, sort of year 12 and year 13. So GCSE and AS competitions, we run several. We run some online ones, some multiple choice ones, and we also run paper ones. If you look at the BPHO website, www.bpho.org.uk, that's an entire listing of the various competitions that we run. Now, you can't enter them individually. You can only enter them via your school. So your teachers will need to register you, and then you can take the competitions once you've been registered. How do you find the grade boundaries? That's not immediately obvious because we don't publish them in general. If you're interested in particular, in a particular year, we might be able to dig that out. So do email us if you are interested in particular. In general, we don't publish the grade boundaries.
Well, we do publish them. They're sent as a report out to teachers, but we don't list all these things.
We don't list them.
It's just it's not really all that useful to you. The competition's over and done with, and it depends upon the cohort who take part. So a different year would have slightly different grade boundaries. So really, you just practice on past papers. That's the key thing, to stop worrying about sort of marks. Do the questions.
Yeah. Yes. Good advice. Good advice there. Any more questions?
Okay. Thank you. We will see you next week, I guess.